Okay. Hello everyone, welcome back to Code Enzyme. So in the last video we solved this problem using prefix sums and segment trees. Now in this video I will solve the same problem using square root decomposition. Okay, let's first read the problem statement again. You are given an array of n integers. Your task is to process q queries of the form. What is the sum of values in range a to b? So basically you are given like integers 2 to 4 here. So 2 plus 4 plus 5. So 2, 3, 4, like the sum is 11. So we have to output the sum that is 11. Okay. Now if you try to do this naively using for loop, it will be in big of n square and that will give you a TLE. Okay. Okay. So now this method, that is in this video we will try to solve this problem using square root decomposition. And actually I should call this block decomposition and not square root decomposition. So we should actually call this block decomposition. Generally we take the size of blocks as the square root of n or the length of the array. That is why it is generally called square root decomposition. Okay, so what is square root decomposition? Basically, let's say you have an array, so a1, a2. So if you have a, let's say, very big array, let's say of 50 numbers, okay, or let's take something which is evenly, like let's say 49 numbers, because it is a perfect square. So let's say the first element is a0, then a1, then a2, and obviously it will go till the last element, that will be a48. Okay, and now I can divide these 48 elements into blocks of size 7, right? So the first block will have elements from a0 to a6. Okay, second block will have a7 to a how much, like 7 plus 7 is 14, so let's say 13. And the next block will have elements from a8 not a8, a14 to a 7 3 is 21, so a20. And then this block will have a21 to a27 and so on. Okay, so you will see that like this is one block, this is the next block, and this is the next block, and this is the next block, and so on. Okay, so we have many blocks like this. In total we will have 7 blocks, right? Because they are assigned 7, and 7 into 7 is 49, and we had 49 elements here. Okay, and one thing you will notice that these index like 0, so 0 upon 7 is also 0, 6 upon 7 is also 0. In here you will see like 7 upon 7 is 1, and 13 upon 7, if you do integer division, it is also 1. Okay, in here 14 upon 7 is 2, and 20 upon 7 is still 2 if you do integer division, right? So let's give these some ID. So let's say this is ID of 0, this is ID of 1, this is ID of 2, this is ID of 3, and this goes on till we have ID of 6, right? Because there are 49 elements. So let me just erase this, right? Okay, now I don't want to store these elements in these blocks. I just need the sum. So let's say we have sum of 0 to 6 in here, AI. We have sum of AI from 7 to 13, and so on. I'm just storing the sum. So this will be an array of length 7, length 7, right? So this will be an array of length 7, right? So let's call this array as store array. So this array will be of length 7, and it will have the first element will have sum of a0 to a6. This will have element sum of from a1 to a7 to a13 and so on. Okay, now let's say someone asks you what is the sum of elements from a let's say from a3 to a19. Let's say someone asks you what is the sum of from a3 to a19. So now what you can do is you can first identify the blocks. So obviously this is from the 0th block, from ID 0, and this is from what, how much, like 19 by 7 is 7 to the 14. So this is from the second block, right? From this block. So or let's take some bigger number, not a19. Let's say someone tells you to what is the sum from a3 to a let's take it to be somewhere like 26. Okay, like that. So what you can do is, first you can find out the sum directly from range a3 to a6, because from this block from which uh, this was there, then I can find out the sum from store, like this a7 to a13. I have actually pre-calculated it in this stored array, so this we can process in big O of 1 time. This might take big O of square root of n time. Okay, this will take big O of 1 time, plus a14 to a20. This will again take big O of 1 time. Okay, then so on till we reach this block, this a14 to a20. Then I will do summation from a14 to sorry, not a14, a21 to a26. This will again take square root of n time. Okay, now summing these, well, again there are at most square root of n elements because the block size was square root of n, so this will also take square root of n time only. So overall your query time is big O of root n only, right? So I hope this was clear. Like what we are basically doing is, whenever we can skip the block, just skip it. So first block we will try to find the sum, like this will obviously, if it is not complete, we will try to do a for loop and try to find out the sum of these elements. Then in the last block we will do the same, like try to do the for loop and find out the sum of elements that were, because the block was not complete. And the middle and these middle blocks we can just iterate using the store array that we pre-calculated. Okay, so that is the basic idea of square root decomposition. Now let's try to implement this in code. Okay, so in the last video we solved this using the segment tree. So in this video let's try to do this using square root decomposition again. Now first of all, what do we have? We have an integer n and q, cn and q. Okay, and once we have these integers, let's make a vector. So a of n for I, cn a of I. Okay, now I need to divide this, like I need to divide this whole array into chunks of length square root of n. So let's first calculate the square root value. Not capital square root, let's say square root of n. Okay. Okay, now that this is done, let's I need to have a store value also. So let's say vector int, and let's just call it store, and the length of the store should be exactly square root of n. I mean n times n, or at least one more than the n. And actually this is not like sometimes you actually just hard code this value to not square root of n but to some value like 10 or 20. Okay, so you need to divide like n upon square root. Okay, like that, and sometimes it might give you an error. So basically we want to have one more length, so there are various ways to do this. Basically what we can do is we can simply add the square root value here and -1, so that will work, or you can simply add +1 in the end, both will work. Okay, so just to avoid any segmentation faults, we can have some more, we can just increase the length of the store array. Okay, now let's loop for the IDs in the square root. So we have, I can just simply copy this whole thing and replace it like this. Okay, and actually I don't want to use the I variable, I want to use the ID variable because these are the ID of each block. Okay, how do you get the now once, since we are traversing on the ID, I want to get the L and R values. So let's say int L is equals to ID times sqrt, and similarly R will be what, L plus sqrt, right, -1, because L plus sqrt will represent the next block, so I will add a -1 here. Now that is it. Now just to show you, like I can I will use my debug template also, so to avoid any errors. Okay, so let's say first let me debug the sqrt value, and when I run this, so the square root of 8 was 2, right? I think it is 2.8 something, but when you divide it, so this whole array will be divided into blocks of 2. So 3 plus 2 is 5, 4 plus 5 is 9, then 2, then 8. Okay. Now let's also see the store array also. If I debug the L and R values for each block, when I do this, you will see like 0 and 1, then 2 to 3, then 4 to 5, then 6 to 7, right? So that is kind of correct. And now I want to traverse from L to R. So let's say I go from L, then I go till R, and I can say like store of id plus equals to a of I. Okay, so this will complete my store array. So let's say debug store. Okay, and when I do that, you will see like 5, 9, 2, 8. That was what we were expecting, right? 3 plus 2 is 5, 4 plus 5 is 9, then 2, and then 8. So this is my store array. Now when we want to query it, like, okay, let's say while q minus minus, I hope I am visible in the video, otherwise I will shift my video. No, okay, so while q minus minus, what we can do is, let's take the int L and R, okay, and I want the zero based indexing, so let's have R minus minus and L minus minus. Now first I need to get the IDs of these L and R values. So let's just call it int LID is equals to L upon SQRT, and RID is equals to R upon SQRT. Okay, now once we have the ID, let's have the answer variable also. So first I want to traverse from the L to the end of this block and add it to the sum, right? So let's say for I in range, I will start from L and I will go till the end of this. So it will be like LID plus 1, the next block, times SQRT and minus 1. So this will give me the and I will also put an equal to, but okay, so this works. So I can say answer plus equals to a of I. Now this works, but what happens when L and R are from the same block? This is simply going to traverse till the end of the block, right? So this will give you a wrong answer. So what we can do for that is I'm simply going to take a minimum of R and the end of this ID. So if L and R are from the same block, it will not move till the end, it will stop at R. Okay, now once I have reached the end, then I want to skip the blocks. I want to traverse in the blocks and simply add the value of that block. So let's say for int id equals to the current id, so LID plus 1, and I want to go till the last block, but not the last block. I want to stop at one block before. So let's say id less than equals to RID minus 1 and id plus plus, answer plus equals to store id. Okay, so this will add the answer for all the intermediate blocks. And now now I need to go in the last block also. So let's say for int I equals to R, not R, the last ID, sorry, do we have RID? Yeah, RID times SQRT, that is the first index, right? And now I need to go till the rth index. So I less than equals to R and then I plus plus, and simply answer plus equals to a of I. Okay, so this is going to add the elements from the rth block. But there is a corner case here, that what happens if L and R are from the same block. We have already added our answer once, so this is, if L and R are from the same block, we will be adding the same elements again, which we don't want. So what I can do is I can just put an if condition, and yeah, now that completes the code. Basically I have removed the corner case, that if L and R are from the same block, then we don't need to do this again. Okay, we don't need to move to the rth block and do this again. I think that is correct. And now let's simply see out the answer variable. and check if it works. So I'm getting this answer which is exactly the same. Let me remove the debug lines and then we will submit this. Okay, so let me remove this part, and when I submit this, when running this is giving me the same output. Yeah, let's try to actually submit this here. So yeah, okay, so it passed because you will see that the time complexity for this code is n root n. Okay, and n is going till 2 into 10 to the power 5, so 2 3 1 2 3 4 5, and if you multiply it with square root of 2 1 2 3 4 5, this value it has 1 2 3 4 5 6 7 8, so it is around 10 to the power it is a bit less than 10 to the power 9, so it is able to pass all the test cases. Okay, so that is why we were able to do this, and I hope you were able to understand the square root of decomposition and implement it also. If you did, kindly like this video, and maybe in the next video I will discuss Mohs algorithm also. So we will try to solve the same problem using Mohs algorithm. Okay, so I will see you guys next time. Thank you.